Hello, everybody. I'm Dominic. I'm leading the application engineering team at Lithoz, where we develop novel ceramic applications for and with our customers. My goal for today is for you to understand the 3D printing technology that enabled this next generation ceramic ELD ring. You will learn a bit about what is possible about the design rules and how our technology can be applied to turn new ideas, new applications into reality. If you consider 3D printing of high-performance ceramics, you will encounter us, Lithoz, because we are ceramic 3D printing. We are the global market leader in ceramic 3D printing with more than 200 machines sold worldwide. We do not provide ceramic parts, but the entire technology to produce them, which means equipment with software plus the materials. Accompanied by this portfolio, we have the proven competence to develop novel ceramic applications together with our customers and partners. This is a selection of the customers who trust in us and in our technology. As you can see, these customers span from general industry like our service providers to aerospace, semicon, medical and dental, as well as research and academia. Our customers in the medical and dental field, for example, produce implants, restorations, and medical equipment. An example for the aerospace industry, you can see are the casting cores to produce turbine blades, and our customers in the industrial and semicon field manufacture all kinds of structural and thermal applications, represented here with a gas distribution, also made from yttria. Now let's learn a little bit about the technology, which is called LCM, lithography-based ceramic manufacturing. LCM is a 3D printing technology of high-performance ceramics. Because we are producing ceramics, it implies that all the major steps of the ceramic process, forming plus thermal treatment, are necessary. In our case, we start with the 3D model, which is printed by our printers, which you can see here. These printed green parts then need to be thermally treated to have the final ceramic part with the desired properties. The core unit of our printers consists of a LED light source exposing blue light onto the optical system, which projects a defined 2D picture onto the vat. The vat is filled with a photoreactive ceramic suspension called slurry. This liquid slurry cures when exposed to the blue light, turning into a solid polymer filled with ceramic particles. The first layer attaches to the build platform onto which the entire part is being printed layer by layer. We use layer thicknesses from 10 to 100 micrometers and pixel size from 10 to 75 micrometers, depending on the 3D printer and, of course, on the requirements of the application. After printing, the part needs to be thermally treated. At first, the polymer, which is still in the green body, needs to be decomposed and removed out of the part. This step is called debinding. After this step, the part only consists of packed ceramic particles. In the second phase, the part needs to be sintered to reach a fully dense part having the desired ceramic properties. This sintering is done at high temperatures below the melting point of the material. During this process, the part shrinks, which can be seen in the picture here of our CEO, Johannes Homer, shrinking about 20 to 20% in size. So this was the core technology. Very important question now is which materials are available. The answer is almost all the major ones. For today's audience, the highlighted structural and thermal ceramics like yttria, alumina, aluminum nitride are probably the most interesting ones. One of our strengths at Lithoz is to develop new materials and tailoring them for certain applications. So there are a lot of varieties and customer-specific materials besides the ones that we can see here. Yeah, to sum it up, LCM allows to combine the outstanding properties of high-performance ceramics with the most innovative manufacturing technology, which is 3D printing. Ceramics are used where other materials fail. They have high mechanical performance, chemical and thermal resistance, and every ceramic has its special electrical, chemical, or biological properties. 3D printing enables fast iterations, as many designs can be printed at once without tooling. It's a flexible production technology, allows for mass customization, and the creation of designs which are otherwise not even possible. Talking about designs, let's learn a little bit about the design possibilities of LCM. LCM stands out in its capabilities to produce lattice structures, features down to the micrometer range, complex internal structures like channel systems, and of course, all crazy freeform surfaces that you can think of. All that from the micrometer up to the decimeter range. One point I want to convey today is our main design principle made possible by LCM is to place material only where it is needed, where it is functional, and get rid of the rest. Here we can see some examples of what's possible. For example, on the top left, you can see a 3D lattice structure with strut thicknesses down to 55 micrometers and channel size approximately 100 micrometers. Or on the top right, another lattice type part like the porous filter, which is assembled into a 1 meter long filtration system for lithium extraction. On the bottom, you can see aluminum nitride cooling plate with intricate cooling channels and lattices, which shows what is possible to produce inside a part. On the bottom left, we can see that also threads are possible in this silicon nitride nozzle. Knowing what's possible is equally important as knowing what is not and what to consider when designing for ceramics. When designing a part which requires LCM, the three components function, ceramic, and 3D printing need to be considered. The function is usually not our knowledge, but the customer's, so I will talk about the other two. When designing parts for 3D printing, one always must bear in mind that the part is built up layer by layer or block by block, like building with your Lego blocks. So overhanging sections above critical length, angles, or masses need to be avoided or supported during printing. And of course, you need to attach the part to the build platform, either by having a flat surface or putting the entire part on support structures. After printing, all parts need to be cleaned, so all areas must be accessible to the cleaning media, which is usually a liquid or an aerosol. If there is support, it needs to be removed, which is often no problem, but it can be tricky, especially on freeform surfaces or in internals areas. As explained earlier, the polymer gets decomposed thermally during debinding, and the decomposed products must diffuse out of the part. Having a low wall thickness and a high surface to volume ratio makes this step faster and easier. The densification of the ceramic particles during sintering to the final properties involves, as mentioned earlier, a significant amount of shrinkage, which needs to be considered. Edges, corners, notches should be chamfered or smoothened, and the wall thickness distribution should be homogeneous to avoid stresses. So overall, an organically open, self-supporting structure with a lot of surface, like we can see here, are a very good fit. Yeah, which finally leads us to the design we're discussing today, which is pretty much approximating this ideal design, the ALD ring and its segments. We see in this part complex nozzle geometries, an internal channel system, lattice structures. All these features wouldn't be possible with another ceramic forming technology. And this self-supporting design with thin walls and homogeneous walls allows for lightweight structures. Thanks to LCM, we were also able to develop fast together with our partners Alumina Systems and Plasway, as design iterations can be tested quickly and in parallel, producing different designs or segments in one run without the need for any tooling. So now I invite you to check your current challenges with components or systems. Ceramic 3D printing is probably a very good solution to at least one of these. Let's solve them by developing your application together. Thank you very much. And now I'm excited to hear from Mr. Wege what amazing things can be done with these ALD rings.
Thank you very much for that, Dominic. Sorry about the technical issues. There, we've got you now. We can see you. But we can't hear you.
No. Something
Right.
always has to not work.
Oh, thank you so much. Right, as you said, yes, let's press on and bring Stefan across. And Dominic, we'll get you back a bit later for the Q&A. So thank you for that. Hi, Stefan.
Hello. So I hope you can see already my presentation. So
we cannot see it yet. I've just closed Dominic's presentation. So perhaps you could launch yours again. Now we're on the stage. Let's get that up and running.
Launch it again.
And then we can get into a bit more of the detail. Right, we've got it launched. There we go. Looks very nice. Right. Okay. I'll leave it to you, and I'll be back after the presentation. Thank you.
Okay. Yeah. So I'm Stefan Wege. I'm the owner of Plasway Technologies, and you will see here a system what is able to make on the one hand ALD, plasma enhanced, and ALE in one chamber. And to do so, and to have this possibility, we need in fast atomic layer processing, and therefore this gas ring what Lithoz is building, and together with Alumina system, is a key component to achieve this possibility to really be on a fast side, that we have a fast atomic layer processing. So just a small overview of Plasway Technologies. So therefore, we are already since 2016 as GmbH on the market. Before, I have a history in Siemens, Infineon, Qimonda, so I'm coming from the microelectronics part. And we still working also on some consulting for, especially for dry etching, for plasma school, parts business, analytical service. And now we also do already contract coating and further development of PE-ALD and ALE in one chamber. So we are located in Dresden, so in the Großritzer Straße. We have a big laboratory where we also now mounting a multi-chamber system with a partner, and so we just moved in 2 weeks ago. So therefore, really first time that I also can give you here some insights. Besides our technology, we also, together with Alumina Systems, we provide special parts, especially a bipolar ECHAC for thermal control on 300mm wafers. And we also supply LiftPins with made of zirconium oxide. I think nobody really can do it at the moment. And we're also building coverings out of aluminum oxide, as I said, together with Alumina Systems. So the basic concept of ALD is that you bring in on your chamber, on your vacuum chamber, first a precursor. This can be a complicated carbonized material, a polymer, and this is sticking very nicely on the surface of the wafer. Then you need to purge, so everything needs to be removed. And then in the second stage, in the third stage, you bring in, for example, oxygen in your reactor to make then an oxygen reaction on the surface, and then you need to purge again. So first of all, you see already is a limiting factor when you would like to make it fastest, bring in the gases in a good way, bring in the gases on the surface, on the silicon, on the surface of the wafer very good. And on the other hand, you have to pump it away. So pump it away, okay, you need a big pumping possibility. So we're using a turbo pump. Not so many people using this, but also for bringing the precursor, we developed a special ring together with our partners Lithoz and Alumina Systems. And here we have again a purge, so therefore 2 times pumping and 2 times bringing something in. And what's also important that we can make the precursor independent of the reactant flow into the chamber. On the other hand, and this was my idea, when we look at the ALD, and this is already since the 16th, 17th, especially developed in Finland, we are now in the phase where we would like not just to make atomic layer deposition, because you can imagine each of the step just bring in one chamber, one atomic layer on the surface of your wafer. When you would like to remove it, this is what the people also would like to do, then you have a similar approach. So for example, you would like to etch silicon, then you can apply some chlorine, but here you need already a plasma to create chlorine, what is then sitting on top of the silicon. So means in standard temperature, normal temperature, this chlorine will not react with the silicon. You need also a purge step to remove all the other chlorine out of the chamber. And then the special trick is you bring in argon. So this argon is this argon ions needs to be accelerated. So in this case, you don't want to have really ion interaction with a lot of kinetic energy. But here we need now interaction with an argon ion that has the right ion energy. So you also need to know how you control your ion energy that you really break the bond, the first bond of the silicon. The only difference is this precursor stuff is, we call it self-limiting. So the precursor is not building, it's not going on each other. So the precursor don't like each other. It's just claiming on the surface of the silicon or whatever you have on the wafer. The chlorine is not self-limiting. So therefore, here it's much more important that you can control the gases in a good way, uniform and also fast. But our idea was to bring this together in one chamber. So we had a special chamber, originally was a deep trench chamber from Qimonda, what we used in the past. This was my last project. So it's a CCP reactor where we can test our fast gas pulsing with this new injection concept. Means what we developed, and this is really the first type of gas ring. We have here this ceramic gas ring, and here you see just the nozzles, and these nozzles are made by Lithoz 3D printing technologies. So therefore, together with some special flow dynamic simulation of the complete chamber, we were able to control in a good way how the gases goes into the chamber. And the specialty on this ring is that we really can bring on the one hand the precursor A here on each of these red nozzles, and the precursor B on the other nozzles. So therefore the nozzles and the gases will never interact with each other. It's just that the nozzle A goes in with this nozzle, and then precursor B with the second nozzle. And this was extremely important to be very fast, because then we don't need to clean, we don't need to pump out the special some interaction channels. But what you can see already here, we were able to bring in the gases very nicely. But in this case, this old chamber has a turbo pump, but is not sitting symmetrically. It is sitting by side. So therefore, you can already see, at least when we turn off the gases, that we don't have a perfect gas distribution function. Then, therefore, we got a nice support from a company who is interested already in a 17-inch reactor, not just 300 millimeters. So then we had the challenge that we need now a ring that has an inner diameter of the order of 500 millimeter. So Alumina Systems will later explain how we did it. So you see it is made out of parts, but we have again the same system with the gas nozzles, so that each second nozzle will bring in precursor A and the other brings the precursor B. Here another picture out of this gas ring. This is the lid of our tool, and here you see how the gas ring is mounted very close to the lid. And here what you see, and this is also special, and here Alumina System has also some special knowledge how to make the gas connection to the two different channels. So this is the gas connection for precursor A and here for precursor B. So you can imagine this is a little bit more complicated also to mount this stainless steel system on this aluminum oxide gas ring. What is also very important for us now that we have a clear indication before we bring in this gas ring into the chamber, what is the performance? So here you see, for example, possibility, this is a uniformity map. In this case, we achieved all in all 3% uniformity of SiO2 deposition, but you see already 2 of these nozzles were not so good with respect to the overall mean value, but means with the measurement of a direct flow of each gases, we have already now also a very good possibility for a quality check of the gas ring. And even now we are able to test each segment before any debinding, etc. So first of all, our FALP system is now a new system where we have on the one hand this 500mm ring. This is what you see here. But we make a complete new design of the gas distribution function in the chamber. So we have a very nice laminar flow, and we have a symmetric pumping. So we put in a turbo pump, a big turbo pump, in the center of the system. So therefore, we have a much better, we have a real now uniform all over symmetric situation. And by the way, some people still using this old-fashioned shower head design for bringing the gases. You see here directly also the problem when you make flow dynamic simulations of this gas shower head, because you have here again a problem that a special room is needed between the shower head and where the gas is coming out. You have here really a dead volume. And then it could be that if you don't create the holes inside the shower head perfectly, that you really get not just laminar flow downstairs. So you have already an intrinsic non-uniformity. And the other problem is that you cannot really do a fast exchange of the gases, because especially on the one hand, the gases can here interact with each other. And this is a big benefit when we have this two-channel system from Lithoz and Alumina Systems. Here's a first picture of our system in May 2022. So this is a 17-inch system, and at that time we really worked with a big 17-inch quartz substrate where our customer would like to have an ALD deposition. And so we work, in fact, this was the first time that we saw light. This is first plasma in May 22. From that on, we developed our processes with this 500mm ring. Later, and this is now in 23, we built an own electrostatic chuck to work with 300mm wafer, to have, even with our 3,600 liter per second pumping speed turbo pump, the possibility to control even ALD processes, the temperature of the wafer in a very nice way. Here are some examples how it looks like. So first of all, you see here an ALD composition of aluminum oxide and silicon oxide. And what you see is the nice conformality of this ALD deposition. So it works very nicely also on this STI structures. But what is maybe also very interesting is this XPS data to look at this stoichiometry over 100 nanometer silicon oxide film and 50 nanometer aluminum oxide film. And if you look, for example, here in the area where we have the silicon oxide and compare the SiOX with the oxygen ratio, it is just flat. This means over the complete 100 nanometer SiO2, we have a very, very nice and very very independent stoichiometry. It just changes when you go in the aluminum oxide, and then you have definitely here also a flat aluminum oxide profile and different oxygen profile, but it is also almost flat. With this system, what we have, we also can change very fast from one material to the other. Again, this is just possible with our new flow dynamic system, but we can also handle in our system 4 different precursors. So for example, here we can build up a sandwich, 2 nanometer aluminum oxide, 2 nanometer silicon oxide, and step by step. And when you make here an yields analysis, you see also very nicely the different stoichiometry of this different materials. So now we come to the etching. The most important topic, besides bringing the gases and besides having a good and uniform plasma, is that your reactor is able to have a very tiny control of the ion energy. So when you look at some publications, especially from Kessel's group in Eindhoven, you find here the situation. First, you etch nothing because you have no ion energy, almost nothing. Then you have a transition region where you start to etch the first layer, and then you have a more or less a flat area before you really come in a standard dry etch area. And to do so, it is very important that you have a very good control of the ion energy. And we did it especially that we have an independent control of plasma density and ion energy by the choose of the right frequency. So I don't want to go into this detail, but in principle, we have already this, for this material, we have an ALE process available. What is nice for an ALE process is that you, on the one hand, can work with ion energy to create really atomic layer directional etching, but you can also work in an isotropic mode. So for example, you have, this is a resist structure after lithography. So in the order of 700 nanometer here is a CD, but with isotropic step-by-step ALE etching, we can bring it down to maybe 200 nanometer. And in our reactor, and this is also a specialty, we can work even at 20 degrees C to deposit directly on the resist an atomic, with atomic layer deposition and an aluminum oxide film. So we can control very nicely here at the site the future CD. And in the next step, we remove here with an ALE step the top plate of the aluminum oxide, also on the bottom plate. We can even then strip the resist, and at the end of the day, you have this structure, and this structure is in the order of 50 nanometer in this case, and we can use this aluminum oxide directly as a hard mask. Everything can be done in one chamber. And a new feature, what we found is what might be also interesting, and we will work the next years on it, is we have this aluminum oxide, like we saw before, but it is possible when you bring in during the deposition some, again, very well-defined ion energy, you can even create, instead of an amorphous film, a polycrystalline film. So here we will work together with the Leibniz Institute here in Dresden to make this really more reproducible and understand how we can control the polycrystallinity. Another interesting part is when you would like to fill a trench, maybe in the order of aspect ratio 25 to 30. So we can fill here this complete trench with a sandwich of a titanium nitride film. And the titanium nitride film we can also play, due to the fact that we can also etch InSitu, we can play with the nitrogen to titan ratio. So we can really create a titan rich film or a titan good barrier film. So if you would like to have a very good interface which is titan rich, we can play with our parameter, and we can have on the one hand a titan rich interface with a good conductivity, and on the other hand, a very perfect barrier film. And then this is maybe the last thing, what is really possible on our tool here, complete what we did in one step. So we start with an ALE to remove the native oxide. So what you see is a silicon wafer. Then we deposit an aluminum oxide film in the order of 10 nanometers, this one. And then we put on this non-conductive film a conductive film, tinitride, then again 10 nanometer SiO2, and then again a 10 nanometer, 40 nanometer conductive tinitride. So in our chamber, we can switch from ALE to deposition, but also from deposition from conductive to non-conductive film. So we can bring in a complete capacitor in one step, and in this case, just in 15 minutes, we make the complete capacitor, which will also fit in a big hole because it is an ALD film. We are working now as a summary on our four-chamber system. We just will start in maybe Q3, Q4 of this year for our customers. So this is a four-chamber system with 300 millimeter. And therefore, the key for our fast atomic layer processing, this is the name of our tool, is FALP, fast atomic layer processing, is the inlet with the Laval nozzles and a big turbo pump. We can do InSitu double patterning with the D-trimming, so we can save here a tool. We can make ALE etching and PE-ALD on different material. And you save another tool. And we can also do PEALD for optical devices. Even 500 nanometer thick films is possible, even on 430 millimeter substrate. And they can do this 500 nanometer within 2 or 3 hours. So therefore, we are really on the way to develop a tool, or have already developed a tool where you can also work in back-end processes, so the temperature is not so high. And this is also just possible due to the fact that we have a very good temperature control via a bipolar e-chuck. And we open up a complete new window with additional ion energy, with an additional kinetic energy to create polycrystalline and maybe also crystalline material. Yeah, thank you very much. This is my talk.
Superb. Thank you for that. So you'll be joining us a bit later for the Q&A session, but appreciate the deep dive just now. So right, let's bring Stefan Walter across. And hi, Stefan, how are you doing? Joining us from Alumina Systems. Please, can you switch on your camera and your microphone, Stefan?
Okay, it's on. So
I can't see you. Could you maybe turn it off and turn it on again? I think during the transition, I think sometimes that causes the camera to go off.
Can you see me?
I cannot. Let me try something else quickly. Okay. Could you turn your camera off, Stefan, and then I'll bring you back across. Okay, let's do that. Right. Okay. Let's see if this works this time. Can you turn? There we go. Right. You cracked it. Right. Brilliant. Let's make sure your slides are working. Then I'll leave it to you to
hold
tell
on.
What
Just
Alumina Systems are doing.
share my screen.
Right, we've got, there we go, that looks very good. Right,
Oh,
we can see you, we can hear you, and we've got the slides, so over
perfect.
to you, Stefan.
Okay. Hello this evening or this morning. My name is Stefan Walter. I'm the head of product and process development here at Alumina Systems in Redwitz. And I'm here since 4 to 5 years together with the guys here and developing new materials, new processes. And together with my colleague, Matthias Freihard, he's joining as well. And Mr. Wambers, he is the CEO of Alumina Systems. First of all, with the beginning, I would like to give a short introduction of Alumina Systems, where we are, what we are doing. So Alumina Systems is consists out of two companies. So one is located in Germany. So here we are in Redwitz. So that's more or less in the middle of Germany. And it was founded in 1950 by Siemens. So this is an ex-Siemens plant, which in production area of approximately 6,000 square meter. And right now we have here something around 130 employees. And since 2022, we have here also battery production site. And also here in Redwitz is located the management and the R&D. And what we have here is also ceramic production, and also metal and copper processing. When we have the ceramic production, our Czech colleagues in Hradec Králové, so this is, they joined us 2012 to Alumina Systems. They have something around 3,000 square meter and almost 100 employees. Redwitz and Hradec Králové they are listed as an equivalent supplier for all kinds of tourista housings for Hitachi. And our colleagues, they are really specialized in copper processing. As I mentioned already, is that we are here in Redwitz, we are doing these, we have a ceramic processing possibilities, but our specialty is later on when we have produced the ceramic that we bring a metal part onto it. So we are able here to make them vacuum tight brazing technologies like active or passive brazing, gluing, glass soldering. With the ceramic 3D printing, I will show you later on. This is the topic of our presentation. And what we have as well is here, before we produce our parts, bringing the ceramic and the metal part together, we do finite element analysis to be sure that all the parts are pretty good after the brazing process. So we serve critical applications like 3D imaging projects, pipeline inspection, high pressure feed-through for natural gas application, like high temperature connectors for nuclear power plants and stuff like that. And that means that we really here serve the high-tech markets, laser technology, X-ray, sensor, oil and gas, and always medicine technology. But the thing is, or one of the important thing is that we develop the parts together with our customers. The customers, they are not ceramicists, and so we have to train with them and to show them how materials are built and how ceramic materials are built together with metal parts. And it's the same here with the ALD ring. So this is the topic now of our presentation. It was also with Plasway that we developed over years this ALD ring. So when Stefan Wege gave you a pretty good introduction about the theory of ALD and FALP, I will give you now an overview how such a ring, so the heart of his machine, is produced. So almost 6, 7, 8 years ago, Stefan came to us and was asking, are we able to produce such a ring with such nozzles? And we started with a ring structure, and the first ring we produced was 2018. It was a slip casting core structure, and only the nozzle parts with screen printed. You have here a magnification of such a nozzle. And it must be done out of ceramic material, because inside the chamber of Stefan's machine, it's the plasma corrosion is that hard that all metal parts will be seen corrosion in a short time. But you can imagine that this is a very inefficient manufacturing process to make this by slip casting. And we said, okay, we try now to divide such a ring into segments. And so what you see here in the middle picture, we have here 8 segments in the same size, almost in the same size. And you can see also here that, or you can imagine if well, so to say, in the former time, we were able to print such a ring in one big piece, but you can only print one. And now with this segmentation process, you can print 2 or 3 rings on a platform just by the segments. And here you have here also what you see here on the right. The right picture is this is such a new design of 3D printed segmented ring structure. So what the task is here, you can also make thinner walls, because of this helps you later on with the debinding process, and will save you also material savings, which is later on something very important for the costs. And yeah, this saves the manufacturing process, because what we see later on is you must have, during the debinding process, as less material as possible. So from the very beginning, we had to start with a development process. The development process starts with a cut design. So we started with the ring segments, and one big issue was to really bring this 2-channel system Stefan told already before. So we have a channel 1 and a channel 2, so where the different gases flow inside, to bring it into this ceramic structure. And here you have to take care about that, always take care about the material reduction in these special relevant areas, to reduce the ceramic volume, because this later on facilitates the debinding process and will give you cost savings for the material of the whole ring. When this is done, the cut design, you bring then the cut design onto the machine, on the Lithoz machine, on the 3D printer. So right now is the 3D printing process. And you see, for example, here over the years from the left to the right, at the very first beginning, we had 4 segments on a platform. Later on, already 7. And right now, also the machine is getting bigger, and if you have an intelligent orientation to bring these segments onto the platform, here on the right picture, already 14 segments on the platform. So this was the technology development of the last 3 to 4 years in the printing technology, really to increase the value or the numbers of printed or printable parts. Okay, so after these parts were printed, you take them off the platform. You have a special cleaning and post-curing process, and then starts the temperature treatment. So you have to, the first step is the debinding process. You have to get rid of all these organic materials in such a printed part. This is the long-term process. Sometimes it needs 4 to 5, or could be also sometimes 6 days. Then you have a material which is first debinded, and then the sintering process has to follow, which has to be very slowly as well. So such a sintering process could take you 2 to 3 days as well. But after that, you have here on the right picture a segment after the sintering process with a density, so this is pure alumina 99.9 material with a density of 3.9 and 92. Such parts, they will be sintered, for example, in a final sintering stage at between 15 and 700 degrees C to get really dense alumina segments. So if you have these segments, we are ready for the assembling process. So we have here a bunch of these segments, and now we bring in the next pictures these ring segments to a part, to a ring. So here we see the ring segments. They here will be now assembled to one ring structure. They will be glazed with a special glass, and when this glue, also this glass is applied here onto the ring, it goes into the furnace in a second sintering step where the glass melts up and brings or fixes the parts to one ring structure. And here on the right hand, this is, I think, Norbert Gall, a colleague from Lithoz of us, shows here the ring after such a glazing process. This is now a very important step, so the inspection process of such single segments and final ring structures. Stefan told you already here, this was one of the first ring structures on the left-hand side of such an ALD chamber. So the ring is here mounted on the lid, but it was successfully processed in a plasma ignition, so that was 2022. But what we see is now these structures on the lid that here between 6 and 9 o'clock we have this uneven deposition of gas. You see this here on the lid structure, and the rest here is more or less good, but we have areas quite uneven. And so we said, okay, we have to get more into the control of such ring structures, and that we have developed a test facility to control first the gas flow of the valves. So what we see here in the middle picture, we have a very smart test facility, very small one, with a gas flow meter. And here we control all the valves and to check if the gas flow is absolutely correct. And if all the segments are well done, we bring them to one ring structure together. And this is now the right picture you see here. You can see now the correct flow of the gases with even deposition across the complete ring area. So for the next generation of ring segments, we are still in collaboration with the colleagues of Lithoz and Plasway technology. And for example, here on the left hand, you see a first generation ring segment. There is here still a lot of material of alumina inside, too much material. And over the years, we were really now able to get new generation of ring segments. They are lightweighted right now, very thin walled structures. And we developed also some new support structures to get this development is necessary to get in results higher geometric accuracy after the sintering process, and also to get higher reproducibility of the whole part. Finally, as a summary, you can say, first of all, we showed you, I'll give you a brief introduction about the 3D manufacturing process of such an ALD ring with 500 millimeters in diameter. So we give you an idea from the way strategy to the prototype and to the final product. From the cut design, we have to completely start with complete new design of such a ring structure to fulfill all the specifications what Stefan Wege needs. So what he needs is a really constant gas flow and a gas distribution in the chamber. Then with the colleagues of Lithoz, so the 3D printing process, which is the heart of the process chain to build off such an ALD ring. So all the experience from CAD design rules or the debinding process during the sintering, all these knowledge must be combined with the 3D printing process to get out good parts. The temperature treatment, well, this is a process. This process incorporates the know-how and years of experience producing ceramic ceramic materials and ceramic parts to get really proper parts at the end of this. And finally, what is really something very important, take care that an inspection and documentation must be implemented. So it's necessary for the quality management and the production process at the end to produce proper ALD rings at the end. Thank you very much for listening to our presentations, and we hope now for a lot of questions, and thank you very much.
Thank you, Stefan, for that. Just give me a moment. We'll bring everybody back to the stage now, and we will be able to embark on the Q&A section. I can see some questions are starting to come in. So I think without further ado, we have extended the event a little bit, but we realized some people may have to leave at the top of the hour. So let's get into the audience questions straight away. Impressive work, says Petar here. Two questions. In what atmosphere is the debinding being performed currently? And the second part to the question is, from a materials or elemental point of view, what are the requirements in terms of part purity? Let me put the question on the stage there if you look for the reference. Dominic, is this one for you perhaps?
Oh, okay.
Yes, so I can start to answer the debinding is done at Alumina Systems, but I assume it is done under a normal atmosphere. Mr. Walter, if you can correct, this is how we suggest to do it, because it's alumina.
Just to fulfill the question, there are in the former time we were debinding such parts in atmospheres like nitrogen or argon atmosphere. Sometimes it's necessary. In new systems, it's now possible to get directly to do the debinding in normal atmosphere. And to second one, from a material element point of view of purity, well, this material right now we are working with a 99.9 material, but I guess that was from the very beginning, starting to go ahead with a 99.9 material. But from our point of view, a 96% alumina material should be possible as well.
We've got another question as well, also on debinding. That really seems to be piquing the interest of people. Have you considered using a catalyst assist during the debinding process to reduce the time?
Not yet.
Not yet.
It's
nice short answer. Good. We can get through lots of questions in this case. The next one we have, here we go. If I can bring this one up. So this question here is, how do you test for parts to be sure that you don't have delaminations? Do you do some sort of NDT process?
You have a special yes, we do. All parts after sintering will be tested in a sort of we call it this is a testing method where you bring in a sort of color material into the part, or you in a sort of bath, and later on you bring it under black light, and here you can see very tiny little delaminations later on. But when you see this, this material is, or this part or this segment is lost, so to say, and you must work with a new one, but you cannot repair this, unfortunately. But it will be tested. There are several tests to test delamination or tiny little cracks and to make them visible as tiny little cracks.
The next question I have is about some of the images which were shown. We could see the support structures inside the printed parts. What are those support structures for, and will they be removed after sintering?
Okay, so the support structures, they are really necessary. This is an important thing to stabilize, first of all, the printing process, because we have very thin wall structures. And another important thing is that we stabilize during the sintering process the sintering process, because you can imagine that such a part, such segment can bow, it bends, and this bending process during the sintering will be stabilized by adding and doing this or stabilizes the sintering process, not bending during the sintering.
Thank you.
It stabilizes the geometry.
I have a question more about sort of, I suppose, what was behind the project, across the development of the gas distribution ring. What was the single design constraints that AM allowed you to remove compared with conventional processes?
I don't know if you really get this question out to me, but for me it was clear when we analyzed how we can make a very fast process, that we need on the one hand a two-channel system, that we will bring independent the precursor and the reaction product in the chamber. We would like to have a very small volume to do so, and it is very important that we have a very good gas distribution function. Therefore, this was really, we did a lot of simulations to optimize then this type of nozzles. So we found already with our flow dynamic simulation how this nozzle should look like, at least at the first stage. And then it was also clear, due to the chemicals what we have in our reaction or in our chamber, or we will have also in the future in our chamber, we need a material like aluminum oxide, but which can withstand, for example, chlorine-containing chemistry, etc. So therefore, I did first the simulation and also the complete development of the idea, and then it was a funny thing to find somebody who can make it. Yeah. And by the way, I had a nice presentation of Lithoz on a special, I think in Frankfurt, it was in a messe. They showed some very nice small structures, and I was so fascinated by the small ceramic structures that I asked them, can you also do a nozzle like this? And then they bring me, but they don't want to answer me. They brought me directly in contact with Alumina Systems. And yeah, I found the right guys at that place. Even in Bavaria, there are really nice people available, and they they listened to me, and they also was fascinating for my idea, and they really are, I think, at that moment thought about what can we do with the 3D printer. So I think I come at the right time to the right persons, and yeah, it took a while, but I think I'm really proud of what we achieved now, and I can tell you the overall concept is working. We have also now a quality insurance, and yeah, still very nice partners.
Thanks. Detailed. Yeah. Go ahead, Dominic.
Add here that those intricate channel systems with the complex nozzle design and splitting the parts into segments which are stiffened by this lattice, which will give reliable sintering results. I think these are all components that really are enabled by the 3D printing method.
Yeah.
And at the scale, we saw the progression as machines have enabled an increase in build volume to adding more components on there. But at the scale you're operating at, the 500mm level, what turned out to be the most difficult engineering challenge? Was it the tolerances? Was it the thermal behavior? Or was it something else?
So first, from my perspective, obviously, and this is what we showed also with this flow dynamic simulation and also the measurement, we really need a very accurate nozzle-to-nozzle characteristic. So for us, really, the geometry of the nozzles themselves is extremely important. And obviously, and Mr. Walter also printed out, even in our chamber, we need a very good and tight control of all the tolerances. Yeah. So we need really a ring, not an egg. And sometimes it was in the beginning also an egg. And so therefore, we really have to work on the overall technology, and especially also this filling structure, I think, helped a lot. Maybe Mr. Walter, you can comment on this, to really know that we are able, that each segment has the appropriate and required specifications.
That's correct. I insist. So because when we do the sintering process, we realize from the very beginning that, as I mentioned already, that during the sintering process, when you have this bending of the parts, you get out of tolerances pretty fast. And that means you have to get in a lot of ideas into to create a new design, or to design it completely, or you need a complete design change to really ensure the proper sintering process, that at the end the part or the segment comes out as you want.
So anything you'd like to add, Dominic?
I mean, yeah, both of them had explained it very well. On our side, on the printing side, it really helped us to move to the bigger build platform, to the S320, where we could, put fivefold throughput on a part per print. This was really a big game changer for us.
I think we've got time for maybe sort of one or two more questions. So if anyone does have a final question they'd like to ask the panel whilst we've got these experts here available, and please do. For me though, I'd like to know, maybe sort of looking ahead, looking beyond gas distribution rings, where do you see the next opportunity for ceramic AM in it could be in semiconductor equipment or plasma tools, or it could be sort of beyond there.
Yeah.
Who'd like to take that one?
What we can see from our side, what really gained interest in the last years is thermal components like the aluminum nitride, where you can manage your thermal behavior of parts, because you have still the very high corrosion resistance, but you can combine it with a thermally conductive material, which is pretty interesting for many applications. And yeah, this is where we see one big interest from our side.
Maybe from our side, we also see, due to the fact that aluminum oxide is already a very nice material, maybe a step to different materials could be interesting, that having even lower sputter rates than the aluminum oxide. So flow dynamic is maybe still the key, but also the interaction with the plasma is another key for the lifetime of the parts. Yeah.
Okay, I think we've got time just for another quick question here. After you've debound the structure, could you infiltrate the pores with another phase?
Yes, sure. We have customers doing that, for example, to change the color, or if we could use the infiltrated silicon carbide parts, there it is the standard process. So definitely that's something you can do and which is done.
Splendid. Well, thank you to everyone who attended and who participated by asking questions. If you do want to know more, then you can get in touch with our panelists. The contact details have been shared, and we'll be following up to everybody who joined today anyway. Also, of course, I want to thank our panelists, Dominic from Lithoz, Stefan at Alumina. Thank you for a very detailed overview. I think you've given us a lot for all of us to think about today, and it's remarkable to see projects in this area of additive, which is maybe slightly less explored and well known than some of the polymer or the metal technologies, but really enabling applications which are just not possible through other methods. So it's delightful to hear about these projects. So thank you all, gentlemen.
You're welcome. Thank you
Welcome.
very much.
Thank you very much.
Great, and I wish you all have a great rest of your day wherever you are. Thank you again.
Yeah.
Thank you. Bye-bye.
Bye for now.